So today we are going to like present this first session of this introduction to ROS. So here is the overview for this presentation, and what we are going to do is essentially get acquainted with ROS. So as such, ROS is it's a collection of a lot of things, and it has like somewhere a direct relationship with Unix or Ubuntu system. So that's why getting started is not as easy, but it is somewhat easy, and we will see. So this presentation is designed so that we have these three sessions so that we learn step by step and we don't miss out on important aspects. So first we are going to talk about what ROS is. We will try to understand, like, if it is going to be useful for your work or not, like, so I'm just going to present this picture, and then we are going to talk about the core concepts in ROS. So suppose you want to pick it up for implementing something, then you need to know these basic core concepts, like, and there are not many, so few. And then we will get our hands dirty in part 3, which is like we'll set up a workspace. So a workspace is just like, just like a project space. So you create this workspace only once during your entire ROS development thing, and then we will create a hello world, or like a very basic program, and we'll see. So towards the end we will have run our first ROS program. Okay, so that is the agenda for this session. Okay, so let us jump into ROS. So ROS is about robotics. ROS is there to help you develop robotic software, robotic hardware, not hardware, but like, to verify and test robotic hardware. So all of these robots that you see on screen, some of these are UAVs, some of these are grasping robots, some of these are like ground mobile robots, and there are like some of these are like smart manipulators. All of these robots are running ROS. Okay, and ROS is like that software component. So if you see a robot, you see something which is tangible, and then there is something intangible which is making this robot work, and that is what what is making these robot works is ROS. So behind the scene there is ROS, which is actually powering all these robots. And some of these robots we have in systems and control lab, like this Pioneer 3D. So if my cursor is visible, this Pioneer 3D we have in our lab. Then this Lego robot, this also we have in our lab. And probably we have like one of the UAVs, which is AR drone. It is not this, but it is kind of an aerial vehicle. So some of these robots we have. We have more robots, but these are the ones which are like supported by ROS. So these are some of the robots, and to see the exhaustive list of all the robots that are supported by ROS, you can just visit this link. Okay, so what ROS is, okay, and I'm going to be like okay, because what ROS is, it might take a while to explain, like it has these multiple aspects, but simply said, ROS is a collection of packages. Okay, a collection of packages as in pieces of softwares which are there to help you, you know simply, like, which are there to help you with robot development. Okay, and ROS stands for robot operating system, and now it says operating system, so there it might create a confusion that it is kind of an operating system, but it is not an operating system. It is kind of a meta operating system. So it is like a collection of packages which help you to do robot development. Okay, but if we speak about, like, what is that essence of ROS, then the essence of ROS is these two things. At its core, it facilitates these two things. First thing is running multiple small programs concurrently. And you guys might have been familiar with this term called multiprocessing. And multiprocessing is basically this same thing, like being able to run multiple processes. So these processes here in the ROS terminology are called nodes or small programs. So these nodes, so the ROS allows you to run these nodes concurrently. Okay, and then the another thing which it does is it helps you to establish communication between those nodes. Okay, so if we talk about, like, in essence, what is that basic utility it does, it gives is this. But not just this, there are a lot of more things it does. But needless to say, these two tasks are very fundamental to all of these robotic tasks. Okay, so in robotics, uh, you need to run a lot of concurrent programs, like because like a robot has to take data from sensors, it has to control actuators, it has to run a control law, it has to run some kind of processing. So all of these things have to happen together. Okay, and ROS allows you to do that via these concurrent nodes, and it also simplifies or smoothens the communication between these programs. Okay, now not just this, there are like lot of more features which are there in ROS, and that's why ROS actually stands out. Like, so ROS is not the only kind of framework for robotics development. There are like lots of different I think robot development platform. Microsoft has its own robot development platform. But ROS, why does it stand out? Like, why is it so popular? Because it is, first of all, it is open source, and second, it has got lot of ready to use algorithms, tools, and robot models. So you don't even need to, sometimes you don't even need to create a robot model or create an algorithm from scratch. Like, you get it from the community. So that is one of the reasons that makes ROS stand out. Another very important aspect is that it supports, ROS lets you program in your favorite programming language. So basically, um, mostly, like, robotics code, if you see legacy robotics code, you will find lot of C++ libraries, like lots of C++ code. Because why C++? Because C++ runs fast. Like, it is like the uh, native execution. So it enjoys this luxury of speed. Okay, so lot of this legacy code is in C++, but nevertheless, because ROS supports multiple languages, you can actually use C++ and Python together. And Python has this side of being high level and easy to use. So that makes it even easier to get started with ROS. Okay, so Python is another aspect why ROS is so popular. Okay, then another feature is that, you know uh, if you are working on a standard robot, like, I showed you a photo of a lot of robots. If you are going to work with one of those robots, chances are that robot models are already available, and whenever a robot model is available, then whatever simulation or whatever program you write in ROS, that is going to work as it is on the actual robot also. So there is not going to be, like, a rewrite or changes that you have to do. It is just like run once, like write once and run it. So that is one attractive feature. And the last point that I have written is something called heterogeneous computing. Some of you guys might have heard this term called swarm robots, or, like, multi-agent systems. So in these systems, what happens is you have multiple, hardwares, or like multiple robots which have processing capability. And now, it is not as easy as multiprocessing to actually make all of these things connect together and do compute in a meaningful way, so that eventually you implement some kind of a control. So ROS actually allows you to do this heterogeneous computing out of the box. And if you want to like understand more about it, like, you can go to this link, and it has like a lot of information. Okay, so these are some of the features, or I can say key features, which make ROS stand out. Okay, and there are like some other attractive features, which is that it is interface to other useful softwares which are like useful for robotics development. One of these softwares is Gazebo, which is used for physics simulation. So earlier I said something about robot model. So this robot model is kind of a it is kind of a CAD model, but it is a CAD based model which can be simulated in a way that it kind of behaves like an actual robot. So there are things like actuators and sensors and joints. So all of these are supported by this Gazebo. Okay, and it comes actually pre-packaged. So we had given or like published some instructions to install ROS in your system, and while you did that, this Gazebo software has already been installed in your computer. Okay, so in the second session we will try out this Gazebo thing, not in today's session. So there is something called RVis. Okay, and this is like very popular for visualizing robot data. So if you are familiar with these things called self-driving cars, then you might be familiar with lidar. And lidar gives you like 3D point cloud data, like how things are in space, in the surrounding of a car. So all of this data visualization is, it's not that easy. I won't say it is very difficult, but it is not that easy also. But the thing is, RVis is there to help you, so you don't even have to write or figure out like how to tackle that. So similarly, there is RQT. It is like UI framework which helps you with lot of I would say like visualization things similarly to RVis, but it has like it is more lightweight. Like RVis is a bit of a elaborate tool. RQT is like a lighter tool. Okay, so all of these features make robot development easy. So that's why ROS is so popular. And again, we can see its popularity from an academic perspective, that this ROS was introduced in 2009. So this was the paper, like this was written by Morgan Quigley and his I guess group. So they published this paper in 2009, and as of today, this paper has 8,286 citations, and this number is just growing. So, that kind of shows its popularity in academia. And okay, so now one more thing, like which makes ROS like a mature piece of software, is that it gets updates very frequently, like periodically. And its update cycle is somewhat similar to that of Ubuntu. So if you guys are like familiar with Ubuntu operating system, then you must know that operating systems, like kind of like a new version comes around like every 6 months in Ubuntu. So similarly in ROS, whenever there is a new Ubuntu version, these ROS guys, they release a new Ubuntu version. And some of these Ubuntu ROS versions are LTS, just like Ubuntu. Some Ubuntus are LTS, like they are supported for a longer duration. Similarly, here also, like we have these different LTS. So if you see, this table kind of tells you about like popularity of which of these releases are being used today, and which are being supported for. So if you see here, like Kinetic and Melodic are the two versions. So Kinetic was like like its share was like 53% of all the ROS downloads. And then in 2020, Melodic also gained popularity, and its percentage share increased to 47 from 26. And I think now the new LTS is this Foxy, which is going to take some time for people to adopt, because whenever a new version is released, sometimes like some things break, like some things which used to work in Kinetic may not work in Melodic. And that's one reason, like why would you want to stick with one distribution. Okay, so this is about like versions of ROS. And like so this table can help you to decide which ROS to pick up for your work. Okay, so that's about ROS. Like that was all about ROS. Now let us take a look at some of the basic ROS concepts. Okay, and I think like it is best to understand these concepts with help of an example. So here is an example graph. So just look at this graph. Okay, so this graph is depicting a ROS project. So a ROS project which is like which involves three robots, and these three robots are being controlled by a like a controller. So you see there are like these nodes and there are these arrows. So like just like a graph, like I mean a ROS package or a ROS project, when it is being executed, we call this layout of this process and the communication as ROS graph. So this term ROS graph is basically what we get once our project is running. Okay, so ROS graph is essentially a graph which is depicting the processes and the communication that is happening. So here if you see this node called gazebo, so this is like a simulation exercise. So this graph came from a simulation exercise. In this simulation exercise there was this gazebo node, let me call this node, and then this gazebo node was sending some data to these three boxes. These each of these boxes represents a robot, a physical robot. So there is this bot 1, bot 2, bot 3, and then there is some inside this bigger box there is a smaller box, and this smaller box says odom, and this is short for odometry. So odometry is like a position information of this robot, and all of this position is going to then another node. What is that another node? There is pose collector node, and then further this collector node is passing this information to global pose, and then global pose is telling each of these controllers. Okay, so essentially this example, what was happening in this example is that there were three robots and they all needed to know each other's location so that they can coordinate. So that's this just shows you like how this how ROS helped like me to kind of spawn this kind of a process, like with three robots and getting their information. So this is just an example. So in this example essentially we got introduced to three terms or three concepts. One was ROS graph, second was the node, and the third was the edge or the communication link. So uh, so in ROS terminology, nodes are programs and communication links are edges. So we won't talk about edges as such, but we will talk about nodes again and again. Okay, and one more thing to see here is this rqt graph command. So to create this graph I had used this command called rqt graph. We'll see how to do this later, but just keep in mind. Okay, so these are the four essential concepts that we need to know, like in order to work with ROS we need to kind of like know these four concepts. So first concept is this ROS core, the concept of ROS core. So essentially ROS is a framework, right? ROS is a kind of a collection of package. It is like a lot of tools, a lot of programs, but how do we get to connect with ROS, or how do we get to start it, stop it, is with the help of this ROS core. So ROS core is the first program that we need to run. When we run ROS core, that's how ROS comes into action, like it kind of starts. So ROS core is essentially a program, and it is like it is its name is ROS core, and also like the command which is used to run it is also called ROS core. Okay, so what it does is it does lot of things, but let us just say it does lot of bookkeeping and it does lot of plumbing. Okay, so this term node discovery, topic discovery, communication between nodes, let us call this plumbing. Okay, so ROS core does two things: it does plumbing and it does bookkeeping. Then there is this concept of node. Like I said earlier, a node is nothing but a small independent program. It can be your C++ file, it can be a Python script, or it can be a Lisp script. Okay, so whatever we write, like So we will write something. So that script will be called like a program, and when it is run it will become a node. So a node is like a small program which has its independent existence. And whenever we say a node, like we should see, like see it as a very self-contained small program that does just one thing, or like a very clearly defined thing. Okay, now see, a node has no meaning by itself, so a node has, like has these tasks. So a node will either do some processing, or it will generate some data. Like, so a node can be a source node, it can be a sink node, or it can be a kind of a middle node. So it can, like do some intermediate processing, take some data, do some transformation, and then provide some data, something like that. Okay, so this node will essentially perform two things for us. It will receive some kind of data if needed, or it can just kind of generate some kind of data. So when it receives some data, we say that it subscribes. Okay, it is a subscriber node. And when it publishes some data, or like it generates some data, we call it a publisher node. So this is just a terminology, nothing serious as such. So a node can do both, it can publish and subscribe at the same time also. But just like to keep a clear distinction, a node can subscribe, a node can publish, or it can do both. Okay, but a node which is doing neither of these, that makes no sense. All right, so then we come to this very important thing called message. So if you are familiar with any of the programming languages, let us say, like C, C++, Python, or MATLAB, or Scilab, or something, so we know that all of these programs have this thing called data to deal with, and data comes in a predefined, or a meaningful for meaningful format. Like uh, like there, a data can be a numeric data, a data can be a, like a verbal data, like a string, or it can come from a database, like so there are a lot of types of data in ROS. It is just a terminology, like we call data as message, and message has different format, just like every programming language has, like character, integer, for float numbers. So similarly, but ROS, because ROS is specific for robot development, ROS contains very special message types like sensor messages, geometry messages. So we will see what are different message types. And then finally there is this concept of a topic. Okay, this is a very important concept, topic. So what topic means is, it is a topic is a very important thing in ROS. Like why? Because in ROS we said that nodes can communicate to each other, right? Nodes can give data, it can take data from another node, and it can pass on data to some other node. Okay, but the thing is, in ROS this communication does not happen between nodes, but rather between node and a topic. So a topic is kind of a mechanism which helps these nodes to exchange data. So basically two nodes will never exchange data directly, they will exchange data with the help of something called a topic. So a topic is like a virtual point, in the communication. So sorry for this, but let me go back a bit. Okay, so here in this diagram, um, if you see, there is this oval, right? So this oval, and then there is this rectangle. So there are these shapes, right? And these shapes actually help you to identify which of these nodes is a topic and which of these nodes is actually a node, like a program. Okay, so suppose my robot wants to share information to this global pose node. Okay, or script, let us say my bot one script wants to send some data to global pose, and so these two nodes cannot talk directly. Okay, then what they need to do is they need to talk through this intermediate node called a topic. Okay, so one of these is a script and one of these is a topic. The difference will become very clear it is not that complicated when we see the program, like the hello world program. Okay, so let me just go through this again. ROS core is the first program. We just need to run it once. It is our way of running ROS. Okay, it is our entry to ROS. Then node is just a regular Python script or a C++ program which is run. It can subscribe, it can publish, or it can do both. Then we have message. Message is nothing but data. So we call data as message in ROS. Then there is topic. So topic is a mechanism by which two nodes can exchange information. So topics do not talk to each other directly because that will be very complicated, and topics actually help remove that complication. All right, so here are like some of the messages that are supported by ROS. So like I said, every programming language has a data type, like it has lots of data, like programming languages have data types to kind of store information, right? So this information can be of different types, and based on those types we have these different containers, like so this in ROS there are these different class categories or classes of messages. So first there are standard messages. Standard messages are like those which are available in other programming languages also. So there is this bool data type or bool message, byte message, char message, empty message, integer 8, 16-bit or 32-bit integers, and then unsigned integer and float. So all of these types. Then there are geometry messages, then sensor messages, and navigation messages. So it's no point going in detail about what these different messages are, but their names convey some kind of a, you know, uh, like some meaning. Okay, like this occupancy grade, if you are familiar with map, like you know how robots navigate, then you might be familiar with what occupancy grid will store. Or let us say point cloud. So this point cloud message type will store a point cloud generated by a lidar sensor, something like that. So all of this is clear, right? Like there is some these names have some kind of a relevance. So in order to see all of the messages which are supported by ROS, you can visit this link. Okay, so let us go ahead and get our first hello world program running. So in this hello world program, like you know, every programming language has a hello world, but in ROS, like we have a hello world in this form. So in our hello world program, what will happen is we will have two nodes. Okay, nodes as in regular script, C++, Python, or Lisp. So we will have two nodes. One of this node is node 1 and the other is node 2. So node 1 will want to communicate this message hello world to node 2. So that will be our first program. So now node 1, we can give some meaningful name to node 1 and node 2. So let us say node 1 is a talker node and node 2 is a listener node. Okay, so there will be a talker which will talk, like it will generate a message, which the message will be this hello world, and then there will be a listener which is node 2 who will listen to this message. Okay, and that will make our hello world program. And before we make this program, there are a few things that we need to clear, like you know, before we move ahead. So first thing is, how many nodes? So two nodes, clear, right? What kind of message do we want to communicate? So hello world is a string, so let us, like you know, use string message. And then what about topic? So like I said earlier, like these two nodes cannot talk to each other directly, so we will need a third party, like a intermediate thing called topic. So let us say that topic is called chatter, or like you know, chatterbox, short for chatterbox or something. So there will be this topic called chatter. And do we want to send this message just once, or do we want to keep sending it repeatedly? Okay, so these are some of the aspects. So let us say we want to send it repeatedly. Okay, so good for us that this program actually, this hello world program comes pre-packaged with ROS. So okay, this is how it will look when we have implemented it. And here you can see in this diagram, this is again, this is the same ROS graph. So if you remember the previous thing, there were like nodes and topics and like graph, But here our graph is very simple. There are only two nodes and there is an intermediate uh, topic which is allowing these two nodes to talk, and that topic is called chatter. So the first node has a name talker underscore some big number, and the second node is listener underscore some big number. So this is exactly what we want. Okay, so two nodes, talker and listener, string message, and string message is a part of std messages, and the topic name that we have chosen is chatter, and the frequency is, okay, there is a typo, this is not 1, let us say 10 hertz, because the example which comes with ROS, it has 10 hertz by default. So let us take a look at how to get this running. So first of all, I hope like all of us are familiar with terminal. So in Ubuntu, to bring up the terminal, we need to press these three keys together, Control, Alt and T. When we press these three keys together, the terminal window pops up, and inside, if you have installed ROS properly, then you can just right away execute these four instructions. And when you execute these four instructions, which are essentially, the first instruction is bringing up the ROS core, the second instruction is running this particular talker.py script. So py stands for this Python source code, है ना? So and this Python file here, this talker and listener py files, these are part of this ROSPy tutorials, which is automatically installed when you install ROS, huh? And if it is not there, we'll help you to install it. Okay, so this ROSPy tutorial is a package which gives you this talker and listener, and then finally in the fourth terminal window we will run rqt graph. So rqt graph will bring up that graph thing for us, and when we are done, we will just press Ctrl C and stop all of these processes. So here is a snapshot. So this is like from my system. So you can see like uh, I am inside this directory called ROS workspace, and we'll see how to create that workspace. But this is how it will be like. You will have to open four terminals and separately run these scripts. And what you will get essentially is something like this. So if you see here, in this particular window, I am running talker, and in this particular window, I am running the listener. So just take a note. So in this talker, this talker is saying hello world here, and then this listener is telling you I heard hello world here. So the timings, the timestamp should be similar. So here you see there is like 489 489959. So here 489959, so yeah, this is the same message. And of course this is our hello world program, but so far we have not written a single line, right? And it's a good idea to actually see like what is making this work. Okay, so let's go back. So this is what we wanted to do. We wanted to create two nodes and we wanted to send hello message, and this is happening here. So all we need to do now is take a look at these scripts. Okay, so these scripts are part of ROSPy tutorial. Okay, so what we will do is we will use this command called ROS CD. Okay, so there is this command called ROS CD which helps you to quickly find ROS packages and go into them. Okay, so ROS CD is like a similar command to CD. In Ubuntu we have this command called CD check directory. So whenever we want to enter a directory, we use CD. Similarly here, ROS CD helps you to quickly navigate to ROS projects. So we don't know where this ROSPy is stored in your system, right? We have different Ubuntu systems. So for me it might be stored in OPT Kinetic somewhere, and for you it might be stored in OPT Melodic somewhere. So ROS CD helps you to, like, without worry, find these ROS packages. So we will write ROS CD ROSPy. It will find this particular package. Then inside this, once we are inside this particular directory of this package, we can find this file talker.py and listener.py using the find command. So find command is a regular Ubuntu program, or like Ubuntu command. So if you see, there is this directory 001 underscore talker underscore listener. This is that example which we just ran, and it contains this talker.py file and listener.py file. So let us take a look at what is inside each of them. Just recall what talker was supposed to do. Talker was supposed to create a message and send it, and listener was supposed to listen to that message. So here is the code for talker.py, and like there are like lot of empty lines, so this might look bigger, but it is like a very small code. Okay, and those of you who are familiar with Python, most of this code is just regular Python, and the important, ROS specific uh, lines, or if you want to see the important lines, then those are line 18, where we are publishing this particular message, this hello world message we are publishing. Okay, and then line 8, where we are actually creating a publisher. Okay, so in line 8 we are using this command rospy.publisher. So whenever we want to send out some information or message, we create a publisher, and here in this publisher we are passing certain arguments. There are three arguments. So the first argument is a string. Okay, a string chatter. So essentially this is the name of the topic that we want to publish to. So nothing much going around here, right? So this chatter is just a name, like it can be anything, like it can be message box, or like it can be a random name, like it's just a string. And then in the second argument we need to tell what kind of message we want to send. So if you see, we want to send the messages of type capital S string, and this we are importing in line 3. If you see here, line 3, we are importing this from standard messages. Okay, so standard messages gives us this string message type, and then we tell the publisher, okay, we want to send messages of string type to this topic called chatter. And then there is a third argument, queue size, which is not of importance right now, we'll understand it later. And then there is one more thing, line 6, where we are actually initializing our node. And while initializing our node, we are passing two arguments. One is the name of the node. So like we decided earlier, the script that will talk is called talker. So this is talker, and then we are passing another argument called anonymous. So this anonymous argument, what it does is it adds that anonymous, it makes the talker unique by adding a very huge number to its tail. If you remember, the name of our node was suffixed by a very big numeral, and that number was added because this anonymous was true. If we do anonymous equal to false, then the name of our node will be just talker. Okay, so why did I not do false? Because this is an example, and this is a pre-packaged example, and this is exactly what you will see in your system when you open. Okay, and you can you can change these different things and see for yourself whether these things are what we uh, like you know perceive them to be. So you can do some tinkering with this code, and you can change the name of your node, you can change the name of the topic, but then you have to be careful to change the name of the topic in talker script as well as listener script. Okay, so another important thing here is, like, we decided how often we want to send this message, right? So to control that frequency of how fast we want to send message, we have to create this rate object, and this rate object helps us to do this timing business. Okay, to maintain or to meet that periodicity. So suppose I want to just publish it at a rate of like one message per second, then I just change this 10 to 1. So essentially this argument to rate is the frequency. So if I say 10, then there will be 10 messages being sent out in a second, and that can be seen. Okay, so rest of this is like regular Python code. This while statement is a regular Python statement. Then hello str, I'm creating a string here, this is also regular Python. Then this rospy.log info, it is just like print, like we want to print some message on screen. So this is line 16, you can just skip. and line 18 is the most important line, because line 18 is doing the publish. So this whenever we do this publish, what happens is our ROS node is going to send a message to this particular topic, this topic called chatter. So this is the contents of our talker script. Now let us take a look at the content of our listener script. And listener script is even short, and the important lines, so most of the lines are similar. If you see the first three lines, they are similar, and they will be mostly similar in all of the codes that you write. So first two lines will be there for all the scripts. So first line is just a directive to the system. It tells like what tool to use to, like, run this file. So it tells you to use, like, Python to execute this file. And then in the line 2 we are just importing ROS.py. ROS.py is our, like, is our medium to ROS. Like without ROS.py we can't do most of this business. We are doing with the help of ROS.py. Here in line 8 we are using ROS.py publisher. In line 10 we are using ROS.py rate. In line 12 we are using ROS.py shutdown, ROS.py loginfo, and so on. Okay, so let us take a look at the listener.py code. So in this script, we see we are doing the same business here in the first three lines. Then we are defining a function. So here in line 5 I am creating a function which is called callback, and this function accepts some data, and then what we do is we just print this data. So rospy.loginfo is just like dumping the data on the screen. So loginfo will accept, what log info will do is it will put this line, I heard percentage s, and I heard percentage s will be replaced by the content of your data. Essentially data has another field data, so data dot data. So what will be printed on screen is I heard something something, like, whatever it hears. And then okay, yeah, here, sorry. So what we are doing here is similar to what we did in Talker. So we are initializing our node. The name of the node is now listener, and anonymous setting is again true because this is an inbuilt example. In line 12 we are creating a subscriber, and this subscriber, just like we created a publisher, now we are creating a subscriber to receive messages. And then we are telling what kind of message we want to receive, string messages, and from what topic do we want to receive. So we want to receive from this topic called chatter. And then finally, what to do when we have received a message. So whenever we have received a message, just use this function called callback. So we have to pass a function here, name of a function. So this function will be called whenever a message is received, and that's all. And then we finally say rospy.spin. So rospy.spin is just there, like, which kind of keeps this program running. So if spin was not there, this program will end and it will just stop. Okay, so this spin keeps the program running so that it keeps listening for this messages from this chatter topic. Okay, so this is the content of these two files. And okay, so and once we are done with this, we would have achieved this essentially, like, so we run the raw score, we run the talker script, we run listener script, and then we run the rqt graph command. So rqt graph command will give us this ROS graph, pictorial layout of this ROS graph. Okay, so at this point, like, I mean, our hello world program is done. Okay, so but again, like, we have still not written a single line of code. So how can we, you know how can we, like, so we are going to do that next. We are going to write our hello world, but before we write our hello world, we need to define or like create something called a workspace. And workspace is like, setting up workspace is just a one time exercise. Like, we don't need to set up workspace every time we want to work with ROS. So workspace is going to contain all your ROS projects. So it is just like a regular folder, a workspace, a ROS workspace, like a regular folder where you keep all your ROS files. But this folder has some additional files that help ROS to uh, kind of like identify and run your commands like with ease. Okay, uh, and we will see. Okay, so we are one important thing is for this tutorial I will call the workspace directory as ROSWS. Okay, this is like short for ROS workspace. So I will create a workspace directory with this particular name, ROS underscore WS. So let's go ahead. These are the three commands um, which will execute. So first command is mkdir, which is like make directory. It's a regular Ubuntu command. Then we will go inside that directory which we just created, and then we will run this command called catkin make. So catkin make command will run if your ROS has installed properly, and then you will be able to run this command. Okay, and when you are done running these three commands, you will see there are two directories which are being created inside this ROS/WS directory. Okay, so and then once you so that's all, like that's all, you have created your workspace and it's like a one-time exercise. So once you run these three commands, your ROS workspace is ready to use, and you will observe these new directories, but you don't have to touch these two directories here, like you do not need to. And you just need to do this one thing which is called activating a workspace. So whenever you are going to work with these projects which are inside your workspace, you have to activate. Activating a workspace is like telling ROS, okay, I am going to, like deal, or like I'm going to work with these packages which are inside this particular workspace, so be ready. So what ROS does is it kind of updates its paths, like runtime path, so that it is able to locate all those scripts. So every time you want to work with a workspace, you have to do this source devel setup.bash. So this command you have to execute every time you work with a workspace, and that might be a bit annoying. So what you can do is you can add this command to your like there is something called a bash rc script. So if you are using Ubuntu, then Ubuntu has a startup script called bash script, and we'll give this information later, like it is just like I'm mentioning it here, so that you remember that you don't have to do this manually every time. You can just add this one line in a file and it will be automatically done every time your Ubuntu starts. Okay, so let's go ahead. This is essentially the same thing in action. So here in the first command, I'm creating this directory ROSWS and src directory inside it, and then I'm cd like checking into this ROS workspace directory, and then I'm running catkin make. Once I'm done with this catkin make, you see there are these two additional directories. This src directory I had created myself. Okay, now there are two additional directories, build and devel. Okay, so that is how it comes up. Okay, now we are going to create our package. Okay, so a little bit of elaboration here. So in ROS, everything is a package. Everything is a package. So whenever we create a package, like whenever we write a program, it is going to be inside a package. It is not going to be outside of package. Like everything is inside a package. Whenever you are going to use a robot model, it will come as a package. Whenever you are going to use an algorithm, let us say a shortest path algorithm or a path planning thing or an obstacle avoidance thing or a mapping thing, it is always going to be in the form of a package. So in ROS, everything is a package. Okay, so to run our hello world program or to create hello world, we have to create a package, and this is the command which is used to create a package. So catkin create package. So this command will create, like it will take two arguments from you. It takes more arguments also, but these two are enough. Like I mean these are like bare minimum. So first is the name of the package that you want to create. So I'm going to create this package called test pub sub. Okay, so we are going to test our publisher subscriber, and then
what is that library we are going to use. So we are going to use this ROS.py. Okay, so we are going to use Python script, so that's why ROS.py is needed as an argument here. Once this is done, then it's a good idea to create a scripts directory so that our script files are separate. So this is an optional step. You can like keep your scripts without like outside this scripts directory also, but it's a good idea to keep things in like well, uh, I think well partitioned or a well managed way. So I'll create this directory scripts, and inside this scripts we will create two files, talker.py and listener.py. So to create empty files we use this command touch. It's a regular Ubuntu command, Unix command. And then this is important, we need to give execute permission to these two files, like this talker.py and listener.py. These files need to be executable, and that is done by this chmod. Okay, so this chmod command is used to give permissions, and we are just giving execute permission to both of these scripts. So this is also a regular Ubuntu command. And then what we need to do is we need to write the same code that we saw earlier inside these files. So inside talker.py we will write the code of talker.py, and inside listener.py we will write the code of listener.py. And if you click these two links you will get those two codes, and you can just copy paste. Because here if you copy paste from this slide, uh, chances are you won't get like the proper space and tab and all that, like, so that's why don't copy from here, but just click on these two links. These two links will give you the talker and the listener script. And then finally when you are done, go back to this ROS workspace and run this command again, catkin make. And when you do this catkin make, it will update all these project entries inside ROS. So this is just like some bookkeeping is needed every time we make changes to our package. And catkin make is kind of a way to notify ROS, okay, we have done some changes now, kind of just verify it and may take a note of it, okay, like this exists. So when we do this catkin make, then ROS will be able to see, okay, we have these two scripts, we have this new package, and then we will be able to uh, access or like execute this package. All right, so here is the thing in action. Here I am creating catkin create package pub sub ROS.py. Then it will say created this file, created that file, and successfully created this and that. And then when I do this tree, what will happen, I'll see, okay, what did it do. So here when I do this tree, you see I have created this script directory, and script directory contains listener.py and talker.py. Okay, and again here this is the overall directory structure. So we created ROS, WS and SRC. Build and develop by created by the catkin make command. Then we created a new package inside SRC called test pub sub, and inside, when this directory was created, these two files were automatically created. What files? CMake list and package.xml. These files were automatically created, and we created this scripts directory, and then we put these two Python scripts and we made them executable. So this green color tells you that these files are executable. And then this src directory was created when we created this project package by default. Okay, so this was automatically created when we created this package. So a little bit lot of work for just a hello world program, but it all pays up. Like because this is the same process even when you are doing like going to do a big ROS project. Like you will have to create a package. So this is like just a regular stuff like it. Okay, so now we are ready to run our hello world program. Earlier we run the pre-packaged thing, like which was like which came in the tutorials, but now we are going to run our the code that we just wrote ourselves. So this is finally our hello world program. Okay, so first we run ROS core, then we open another terminal window, we run this talker.py script, then in another window we run this uh, listener script, and then finally we run the RQT graph. And once you are done with this, um, that will be, I think, your hello world script running. So a little bit one missing information is that whenever you open a new terminal, right? So running ROS code does not require you to activate your workspace, but your workspace activation is required when you run these two commands: ROS run test pubs up and ROS run listener and talker. Why is that? Because this package, the ROS does not know of this package. Okay, it only updates this information when you run this activation command called source devel setup bash. So like I said earlier, you don't have to do this if you add this to your bash rc file. It will be done automatically whenever you open the terminal. So but if that is not there, before running this ROS run command, you will have to do, you will have to go inside your ROS ws directory and then just run this source devel setup.bash. Once you are done with that, then you can run ROS run, and then whenever you just need to type the first few characters like TES, and then you can press tab and it will automatically complete this name of the package because you did this, like source devel setup bash. Okay, so that's the benefit of doing this activation. Like it keeps in mind what packages you might use and like what their names are and all. So okay, that's our hello world program. And now let us take a look at some of these commands that we use. So just now we use this ROS run command. So ROS run command uh, is used to run a single script. Like, so here in our hello world program we had two scripts, talker and listener, and we use ROS run in separate terminals, okay, one by one. Now there is this command called ROS launch, which can actually launch a whole ROS graph. A whole ROS graph means lots of node together. So ROS launch can actually help us in reducing this number of terminals that we are opening. Like, so here, like, every time we want to run something, we are opening a terminal, and that's insane. Okay, but we don't need to do that, and we'll see how to modify our hello world to use this ROS launch facility, so that we just have to open one terminal and no more lots of terminal management business. Then there is something called this command called ROS topic. It is a very very helpful command, and we will use this command probably in the next session. But this command is there. It helps us to do inquiries about, lots of aspects of these running nodes. Suppose our talker and listener are running, and let us say, like, I don't know how often it is sending message, what kind of message it is sending, to whom it is sending. All this information we can know by using this ROS topic command. So suppose I download a package from internet, like, kind of a project, and I don't know what this node is doing. So I can use this ROS topic command and find out, okay, like, what this node is publishing or subscribing, what kind of data it is publishing, how often it is publishing or subscribing. All that information we can find out using this ROS topic command. And ROS CD is like very useful when you are navigating. So suppose I don't want to go into ROS WS, then SRC, then test pub sub. Then I can just use ROS CD. I can write ROS CD test pub sub. It will directly take me to that directory. So ROS CD is very helpful in navigating across this ROS workspace. Great. So there are like lots of other ROS commands, and those commands are there in the last page of this slide. So we'll upload this slide after this talk. So you can see like all those commands. So now let us do a little bit of modification. So we have run our hello world program. We created a test pub sub package. We created those listener and talker script, but then we had to open so many terminals to run each of them individually. Now what we can do is we can create a launch file, and the launch file will launch the ROS core, the files, the listener node, the talker node, and everything. Like from so it's like one place, and everything will be run. So how to do that? So again, we will need to go inside our package, our test pubsub package directory. Then we will create a regular folder called launch. Okay, and inside this launch folder we will create a regular file with the name pubsub.launch. You can name it something else also, but you have to suffix it with .launch suffix. Yeah, append this suffix. Okay, and then just open this link and copy paste the sorry, this is the content of that link. And this is what you are going to write inside that launch file. So there are only 4 lines of code, out of which line 1 and line 4 are same almost. Like this is a XML file, and XML stand for this extended markup language. And it's just a format which is used in HTML also, like it's similar to HTML. Like there are these angle brackets, and then like there is this hierarchy where this launch is a parent, this node is a child. So yeah, like that. So okay, we ignore 1 and line 4 because it is going to be there. Line 2 is important. What line 2 is telling is, okay, now create a node. The name of the node should be talker, and where should this node come from is from this particular package. So this pkg is for package, and the package name test pubsub. And then what is that file that actually has this code, and that file is talker.py. And lastly, where should the output be displayed? Okay, so the output should be displayed on screen. So output is equal to screen. If we don't write this output is equal to screen, then no output will be printed. Okay, so that log info command we used, okay, you might not remember, but there was a log info command in the talker.py file. So that log info command, what it was doing, it was printing some message on screen. It is very helpful when debugging our code. We print out these messages, and it gives us an idea, okay, what the program is doing wrong or right, like so this output is equal to screen is just an argument which tells it to dump the output on screen or not. Then we are creating another node which is going to be a listener node. Same thing, like just specify the name of the node, specify the package where this node is, the script is, and then tell us the name of that script file, the listener.py, and then output is equal to screen. And that's all. We have created our launch file. So here we have created our launch file, we created a launch directory, we created a regular file, and then we added that 4-line code. And now again we need to do catkin make, so that we notify the ROS, like we notify ROS to update the project entry. And then now we when we just run this new, now we are ready to use this ROS launch command. And then again we type ROS launch, name of our package, and then the name of the launch file. Okay, so pubsub was the name of our file. So pubsub.launch will run our node. Okay, and then once we are done with that, this is how it will look. So here I have done ROS launch, test pubsub, pubsub.launch, and then it will automatically see, it will bring up these two nodes, listener node and talker node. So test sub pubsub listener, test pubsub talker. And once it is done that, it will start dumping this data. So if you remember this hello world message, it was being printed by talker node, and then listener was printing, I heard this and that, I heard this and that. And you can see this guy is listening. So here 5891 5891, and then 5892 5892. So you see, like it's synchronized, like so there is not much delay. Okay, so to wrap up everything, let us just do one last thing. Okay, so let us modify our hello world program, because so far like we have not really done anything, we have just copy pasted the hello world script. So it will be a good idea to at least like do 2 lines of modification. Okay, so we are going to do that now, and this is like optional anyways. uh, we have understood how to set up our workspace and how to create a package and how to write script and how to run a node and get our ROS graph in action. So this little bit of modification that I propose is that we modify our talker node, we modify our talker node to accept the kind of message, so earlier, if you remember, our talker node was just saying hello world, hello world, hello world, right? Now I want our talker message to accept, let us say, like two different messages. Okay, so here in this picture you see, now what I want is, I want to have like these two nodes. One node will be a cat node and the other node will be a dolphin node. Okay, and then this cat node will send a cat voice kind of message and dolphin node will send a dolphin voice kind of message, and then listener will just do what it was doing earlier. Listener has like no change. Okay, but now the important question is, how much of the earlier code do we need to modify? Okay, so do we need to create two new node files, or can we just use this previous file and just modify it, minor modification and make it run? So we can do that, we can use the previous code, the code of talker.py. Anyways, listener.py will not change, only talker.py will change. Okay, so now what we will do is we will modify our talker.py. But to get an idea what we are going to do here, um, here is our new launch file. Okay, so before we have done the modification, let us just try to see what it will be like. Okay, so here 1 and 10, line 1 and 10 are same. If you remember, line 2 and 3 are some new commands. So these are like argument uh, argument type of this childs, so this launch is like a parent tag and this is like a child tag. So we have two new tags, arg tags, and this arg has this property called name, and name is like an argument because this tag is an argument tag. So name is dolphin message and this the another ones is cat message. So when there is dolphin message, it is having this default value called click and squeak. So whenever I'm going to use the dolphin message, it is going to stand for click and squeak. Whenever I'm going to use cat message, it is going to stand for meow and purr. So essentially this is like, if you remember C++ or MATLAB, we create these variables. So this is equal to creating dolphin message is equal to click and squeak, cat message is equal to meow and purr. It is like that. Okay, so we are just creating two variables with these strings. So dolphin message is a string, click and squeak, cat message is a string, meow and purr. Now we are going to create three nodes, right? Earlier we had only two nodes, talker.py, listener.py, but now we have cat.py, not cat.py, but like cat node, dolphin node, and the listener node. So here in the dolphin node, I'm going to see the same package test pubs up and even the same script talker py, but I will modify talker. Okay, so that's why I have written the name talker underscore mod.py, and the same thing will be used for the cat node also. See, talker mod.py and then test pub sub package. But what is different is this last command arguments. So in the last command, I'm sending dollar parenthesis arg space dolphin message, dollar parenthesis arg space cat message. Okay, so basically this guy is receiving this dolphin message click and squeak, and this guy is receiving meow and purr. So basically we are telling, okay, what kind of message you need to pass. So this is called argument passing, and this is like a convenient way to pass arguments to your scripts. Okay, so the good thing is we are using the same Python script to pass these two different types of messages. Okay, so less modification. And now here is the modified node. And what is the modification? So here in line 20, if you see in line 20, earlier we did not had this sys.rgv thing. This is the Python way of accepting command line arguments. Okay, so when this script is run, this launch file is going to add this command whenever this is going to use this script. So that command is going to come via this argv method. Okay, so this argv will return us the command, the argument we passed. Then here, see, this talker function is here, so this greeting will take value, so greeting will contain whatever message we gave. And then when we are going to publish, we are actually creating hello string. Now we are changing our string to this greeting string. Here we are just putting the greeting inside our string, and then we are publishing this greeting. That's all. And this code you will find inside this link. When you click this link, you can just copy paste this code and you are good to go. And like, it's a good point to verify, like, if you are able to run this code, and if you are able to see those two messages, like these two messages, like, cat and squeak, mew and purr, and your listener is able to print these two, then you have done everything correctly. And okay, like, you have implemented the hello world program properly. So at this point, I think we can stop now, and let us just quickly summarize what we have done. So, we kind of we saw these concepts, important concepts of ROS. What are nodes, topics, messages, publishing, subscribing, ROS graph, right? These were concepts. Then we were introduced to some tools like ROS core, which is the how ROS works, or like, in action. Then there is this command ROS run, which is used to run individual scripts. Then there is ROS launch, which helps us to run a lot of scripts together at once. Then there is this ROS topic, which we did not use, but like we got some idea, like it will help us in future. Then there is this RQT graph. So RQT graph will produce that layout, that GUI, which shows what nodes are there and what communication exists between those nodes. Then we established or set up our workspace. It was a one-time exercise. And then we first saw a inbuilt hello world program, and then we created a replica of hello world program, and then we modified the hello world program to accept arguments and run with launch file. So that's all. So that's what we did. And here is that cheat sheet I was talking about, like what are all these ROS commands, not just ROS commands, but like these cmake list commands also, and some ubuntu command also. So this is for kinetic version, and if you want to see these commands for this other ROS versions, that can be found in this link. So at this point, okay, like I guess we are done with this presentation, and if there are doubts and questions, let us hear them.
Hello, am I audible?
Yes, you are.
So my doubt is, little bit basic. The thing is that why do we need a launch file?
Okay,
Because we
yeah. Yes, go ahead.
yeah, because we already have that earlier method, no, to do ROS launch and then put the name of the two what you say nodes. Then it can. So why do we need a separate launch file?
Oh, you cannot use ROS launch and run like two scripts. So essentially, I think you are referring to ROS run command, right? So ROS run command can accept these arguments like individual script. So with one ROS run, you can run like, one script, and then you will have to open another terminal to run another script. And like, in a bigger, I think, ROS project. Let us say you are doing some robotic task. You might need to run like lot of these nodes, as well as you might need to configure lot of variables. So right now we saw a very simple use of launch file. So launch file can be very complex also, like it can actually help you to load map information. It can help you to configure something called like, parameters. So when your ROS graph is run, you might want to send some parameters. So all this facility is provided by launch file. So launch file, it helps you to kind of like make it easy to run your ROS graph, like
So, uh, can we infer that ROS, this launch file is used to selectively run certain nodes if we want?
it can be, yes.
And if you see the codes when we are passing the arguments, etc., it
Mm-hmm.
is a bit complicated. So when we are trying to make our own package, so where to start with? Like if you want to do something complex, how to start with?
Uh, I think it is the same process that we followed in this Hello World program. I guess once you have figured out like what you exactly want to do, you will you will do this. I think incremental development. You will write your first node, then you will verify whether your node is working as you expected. Then you will write your second node. Then you will, you know, incrementally keep adding nodes and you will keep verifying. And once you are done, you can create a launch file and then everything can be run at once. That's how usually it happens.
Okay, thank you.
Yeah,
Vivek,
welcome.
shall I button?
Yes.
Deepak here. So, like in continuing with the Radhik, question Radhik posed regarding creating our own complicated packages. So, what we would like you to do is, so like these slides will be shared immediately on the Teams. For tomorrow's session, implement like whatever was done in these slides. So maybe so tomorrow's session again will start at 2:30. So we like I will be available from 2, let's say. So from 2 to 2:30, if you have any questions like regarding implementation of things that was discussed today, you can present it. So Vivek, maybe you can give an overview as to what tomorrow's session will be about. So we are, I
Yeah.
mean, today was just a hello world. So we will be making it more and more complex over the next 2 sessions as well. Yeah, Vivek, over to you.
Sure. Okay. So yeah, so in the next session, we will in this session we worked with entirely with ROS. So the objective of this session was to introduce you to ROS. Okay. So I guess Hello World is the best way to see how different pieces of ROS work together. Like you create a package and you create a node. In the next session, what we will do is we will use a robot model. So you will see a robot, a ground robot, a differential drive robot, and you will control that robot by creating nodes, and you will make that robot do something or follow a trajectory, and that will give you a better, I think, understanding and perspective of how to use ROS. So yeah, so in the next session we will use a robot model, and we will see how to use gazebo, or how gazebo is used, and we will see how to do some trajectory tracking with a ground robot, differential drive robot. Yeah, hello.
Any other questions?
Yeah, am I audible?
Yes.
Yes.
Yeah. So, what is the significance of catkin make? I mean, do I have to use this command every time before the uh, ROS run, or just once
No,
when I
no,
modify?
you exactly when you modify something in your project. So what happens is um, right now we are using Python scripts, right? We have not used C++ source files. So if you remember, C++ files need compiling, right? And Python script do not need compiling. They are interpreted at runtime. So what happens is we do not see exactly what catkin is doing, catkin make, but catkin make, what it does is it builds your source files. So whenever you have C++ packages or C++ files and you do some slight modification, your source needs to be rebuilt, because C++ files cannot be executed in runtime. They have to be compiled and then they have to be like built into a binary file so that it can be executed. So all that thing is taken care by catkin make. So whenever you make a change in your project, whenever you introduce a new file, whenever you create a new launch file, all this thing book like this I should say like this record keeping is also done by that cat can make. Okay, so when you run cat can make, it kind of refreshes your project's entry. Okay, your project has this file, and this is this executables, and so it allows you to like quickly see okay this package is there and you can run it. So in short, answer is it is important to run cat can make whenever you have done a modification to your project package.
Yeah, okay. And actually, while using, I was get confused about like storing the multiple scripts. Like they all of them get like distributed in multiple files. So, can you please suggest some streamlined path to store the files in proper packages? Like,
So in this tutorial, what we did was like we created a workspace, right? And inside that workspace, so there was a slide. Okay, let me just go to that slide. Okay, uh, yeah, this slide. So in this slide, if you remember, like there is this hierarchy. Uh, this src directory, right? This src directory is the directory that is like the container for all our projects. So I only created one project, so there is this test pub sub. Okay, and if I had created more projects, then they would just come in this tree, and inside that project then I have again scripts, launch files, world files, robot model files. So that's how this hierarchy will help you to organize different ROS files, because ROS involves all of these different types of files. It becomes messy, and there is no other way than this. Like you have to make this organization yourself. So did I answer your question? Like,
yeah, I mean, okay, like if you have some multiple projects, so we have to
uh-huh.
make some, multiple packages, right?
Exactly. In ROS, everything is a package. So it's like if a package, you create a new package when like you are working on a new project, right? Or you can just copy the old package and keep modifying it, like version one, version two, something like that. Or you can use like GitHub if you know like Git version control. So if you know Git, then you can just make changes and keep committing. You will know like.
Mm-hmm. Yeah, got it.
So, just one thing I want to mention is, see, ROS does not enforce a lot of things. Like, we are independent to use all the features Python allows us to use. Like, so it's like we can use NumPy. Like, we can use NumPy to process some data, and we can like use matplotlib to plot some data. So the good thing is ROS does not stop us from doing what we usually do with our Ubuntu and like Python. Like we can use GitHub and we can also do a lot of other things. It is not going to restrict you from using regular Ubuntu and Python. Okay, it is only going to add you like provide you more features. So that is one thing to keep in mind. So do not feel like okay I'm using ROS so I can't do this or that. Like you can do whatever you can do in regular Python, you can do here.
Vivek, I just want to add
Yes,
on. So,
yes, it,
I mean, with regards to creating files and where you should store them. So, ROS, I mean, currently we had two scripts like listener and talker, which were in the same project, rather, I mean, in the same package, test pub sub. So, suppose they were in different packages, like let's say test pub sub 1 and test pub sub 2. Even then, like ROS would let you communicate between the two. So, you I mean, there is no restriction as to, let's say, you want a subset of files for one particular task and another subset of files for another particular task. You don't need to like create different packages every time with those subset of files. So you can communicate across packages as well. Okay. Yeah, that's what I'm.
Okay, like I mean, my doubt is like if we have listener package in testpub sub 1 and a the talker script in the testpub sub 2. So
Yeah.
is it possible to communicate between
Yes, you can talk to in listener and talker can talk with each other via. So when you uh, like you have that ROS run and then the package name and the script name, right?
them?
So in the package name, you need to specify the appropriate package.
Okay.
So
Uh,
even in ROS launch, you can like when you add a particular node, the entry corresponding to a node, you need to specify a package. So you can like let's say in testpub sub 1, you create a launch file, but it can have the launch file can have entries from some other packages as well. So that's completely allowed.
Okay.
so just want to add a bit. So in the next session now we will do exactly this. Like we will use a like a readily available robot model. Like we will not create a robot model. Like it's a bit lengthy process. So what we will do is we will use a pre-packaged robot model, and we will exactly do this what Deepak just said. So we will be using a model from some other package. So this is usually done, like this is how things usually happen. And so it is a good question that you ask this. So for example, let us say I have a robot, right? Now I want my robot to be able to do path planning, and suppose I download this package which helps you to path plan. Then what I need to know is what are the topics, what are the messages that these two need to communicate in order to be compatible with each other. Once I have figured that out, I don't need to modify that path planning package. I just need to modify my package so that it is compatible with that path planning, and then my robot can do path planning using that package. So exactly that is what we do. Like we use lot of projects and we kind of establish communication between them. And ROS kind of allows you to do that in a very robust way. And why robust? Because even if something is failing, it will not bring down the whole ROS graph. So what I mean is if a node goes off, it will not disturb the rest of the system, and that is one of the powerful features of ROS. So suppose you have made a very big robot like a biped, and it has shoulder motors, it has elbow motors, finger motors, and then it has waist and legs and all. Suppose one motor goes bad or one node goes bad, which is like controlling your grasping, then the rest of the robot will not fall, like it will still keep running while that hand motor might not work, like so something like that. So it makes it robust, like so the ROS graph is kind of very robust to this, and you can just run and rerun like different packages, different files from different packages. Okay, I'm done.
And also, is it possible to make a different package inside some other package like
But why
this
would you
test
do
pub?
that? I think it might cause some error. I have not done so, so I cannot say for sure. But why would you want to do that? Like inside a package, creating another package might be possible. Might be possible. I have not done that. Like,
Because in my practice I did this multiple and because I was get confused in SRC. So there
uh,
are SRC in each this package also and then that ROS
uh,
workspace also. So
yeah,
Acha.
yeah, yeah. So, okay, Deepak, go ahead.
Okay. So the SRC in ROS workspace, the upper one, the one on the fourth line over here, I mean, that's where you put in like all the different packages. The SRC inside a particular package, I mean, that's mostly immaterial unless you're working with C++ codes. So if you're working with C++ code, then that's where your code should go in that SRC in every particular package. Now, the idea of a package is a collection of scripts or let's say worlds or URDFs. URDFs are robot models. So a collection of these which can which stand for something independently. So let's say I can create a package for a robot. Now, what that package will have is the robot model itself. In addition to that, I can have like a couple of scripts which will let some other packages to communicate with this particular package, this particular robot. So that's how you create a package. So everything that you can think of as an independent set of scripts or independent set of files, you can put it in a package. So a package can have just one script as well. So there's nothing, the lower bound is one script. So you don't need to put multiple files into a single package or create sub packages as such.
Got it.
One continuing question on that, if I may.
Yeah.
So in the SRC, we have one package, that is this test underscore pub underscore sub. Okay. So in a particular ROS workspace, there can be many packages, right?
Yes.
So like I am making a workspace for a surgical robot. I can download many packages from internet and then put it up into one workspace. Suppose I am making another robot, then that robot has to be another workspace, right?
No, it need not be. So as long as your names are different, as long as the name conflict does not arise, you can put it in the same workspace.
So workspace is actually kind of one project. Inside one project, you are having this like that.
I would say package is the project level. So workspace is for the system. For it's like you have this home directory, right? Or in Windows you have like local disk C where you put your all your OS files. The workspace that you create on your system, you can imagine in that fashion. Okay, that's where all the ROS files are available.
Acha, so inside this computer, ROS underscore workspace will have all the files.
I mean, okay, so the thing that gets installed is somewhere else, but whatever files you create, you can add in this particular workspace.
And I can also create another workspace also if I want.
Yes.
So let me add this. So like nothing stops you from creating multiple workspaces. The thing is that whenever you are working with a workspace, just activate that workspace before using that. That's all.
So if you have two workspaces, you need to activate both of them if like there are scripts which talk to each other.
Deepak, I'm not sure if activating two workspaces at the same time works well, because whenever you activate a workspace, the paths get changed to reflect that only. Like, so you cannot work simultaneously with two workspaces. That's what I believe.
So, okay, to my understanding, it's just appending to the path. So I think it should be good because I believe I have used it in that manner.
Sure.
One more doubt I had from the tutorial. So when we are installing the ROS, there is some section called where they are asking to set up the environment. Okay, so there is some shell script inside that, bash script inside that, which we have to do. So by doing that, every time my terminal will have like this, or whenever I'm opening a terminal, I have to run that bash script.
Which one? Can you
just
installing?
Post
so
it in the chat.
Okay.
Acha, environment setup you mean?
Yeah.
Yeah, so that's what he was talking about. So that's the activation thing happening for the packages which are installed when you download. I mean, when you download and install ROS. So source/opt/ROS/melodic or kinetic/setup.bash. That goes into bash RC.
Okay, so that I have to do every time when I'm opening a terminal and I want to run ROS.
No, that happens once. So if you put it into bash RC, every time you open a terminal, it's automatically going to be executed.
Okay, so now my question is like, if I'm doing that and now I'm just like that opening my terminal to do something else, then will ROS automatically open?
I'm sorry, I didn't get this.
So let me answer this. So what happens is, like Ubuntu kind of like keeps this path in memory, right? So what we are doing when we say source setup forward slash sorry devel forward slash setup dot bash, what it does is it kind of configures those spaces in the memory. So it's like it is not running something, but it has stored, like it will use some, maybe like some kilobytes of your RAM, but it nothing will be run. ROS will only kick into action when you run ROS core. When
Okay.
unless you run ROS core, nothing is running. It is just configuring the paths.
Okay. Yeah. Thank
Yeah,
you.
you're welcome. So are there other questions, Deepak?
No man. Okay, there's nothing posted in chat.
All right. So even if you get questions later, like you can
Add to
keep
the teams.
them.
Yeah.
Yeah, you can add to teams, or you can ask them tomorrow, like in the next session. So we have
Yes.
overshot by 15 minutes, I guess. We should.
Yeah, we can wind up.
All right,
Uh,
all right.
Harsh, over to you.
Okay. Thanks, Vivek and Deepak. Thanks a lot for your time, and thank you everyone for joining. So I hope you got some learning today, and you will continue in other sessions also. So thank you and goodbye.
Thank you, guys.
Thank you.
Thank you, everyone.